Okay. Hopefully the stream should be starting in any moment. Okay, cool. So, let's see. Let me wait for a couple more minutes to more people join. Then we will start. I probably need to move that over to that. And no, I do not want that. Okay. Okay. Yeah, I might as well not. So, I think I think this is about it. I'll keep about it for people who are going to join for now. I'll keep an eye on the streamer chat. So if anyone has any questions, you can make sure to ask me there. Okay, let me also enable. Okay, cool. I think everything is go. We will start at this point. So, hello, everyone. Oh wait, before I start, actually, is my audio good? Okay. Just if anyone wants to reply to the chat. If my okay. Let me make sure OBS is up. Is the people on Discord, can y'all hear me clearly or no? Hello? Okay. Okay, cool. Thanks. So I will start. So today I will be introducing a little bit about reverse engineering. And if you haven't noticed, I basically, thanks to some people from Purdue for allowing me to borrow their slides for the reverse engineering. So yeah, this primarily this is from another CTF team, which I borrowed and I modified a little bit. So today we will start I'll be starting a little bit about how to work with reverse engineering. So what is reverse engineering? So obviously there's that official Wikipedia definition, but all I'm going to focus here is just say it's just about how something works, and often you don't have documentation. So you're often like kind of in the dark trying to figure out how to figure out what this program is doing. So what types of reverse engineering are we talking about? So there's like 3 different types. So obviously there's the one where you're looking at other people's code. So you're usually having source code here. You're also having like, maybe if you're looking at like PCB or like hardware stuff, that's also reverse engineering. But the one we really are talking about is just looking at how a compiled program works. Hold on a sec. So, what is in a computer? So, throughout this lecture, I'll be mostly referring to the x86 64-bit because those are the machines that are most commonly used. So, like your PC, most Mac devices that aren't like the super new ones, most like laptops, desktops, they all use this particular architecture. And they're also relatively simple. So here, when we're looking at x86, we're going to refer to the main parts. You have the memory, which is RAM memory. You have the cache, which generally is transparent, so we generally don't need to care about that. You have the registers, which is also essentially are just variables that built into the architecture that's very fast access. So you have the general purpose registers, AX, BX, CX, DX, SI, etc., etc. And then at some point, we just ended up numbering the registers from R8 through R15. Go figure. But we also have the some special registers, RSP, which is used as a stack pointer. We're going to talk about stack later on. An RIP, which is the instruction pointer, and it's just basically is the register that tells what code we're executing at the moment. We also have a special type of register, which is a flag register. R flags, E flags, they're the same thing. But generally, they have some interesting, contain some interesting states about what the current processor is. And like these flags, we will talk about how they're important later on as well. So there are other things in the hardware, software that we're not going to even start going into. So we are just going to skip over that. And that's really only if you go deep into the architecture or deep into kernel or stuff like that. So von Neumann, this is, if you've been to any university class that covers operating systems or programming languages, you're probably familiar with this. This is basically the architecture that is used that is kind of modeled for our x86 architecture is modeled after this. You basically have some input, and then you have some memory that contains both the your code and your data, and then you just execute based on that memory, and then you have some outputs. So I'm going to briefly discuss how we're going to look at different data, how we're going to represent numbers. So we have the most basic ones like decimals, which is just what you're familiar with. You have hexadecimal, which is slightly different because they have a 16 base instead of a 10 base, what we're familiar with. And then you have binary, which is a 2 base one. And then they have the specific prefixes. So main takeaways. So if you learn nothing else, these are probably some of the most important things that I'm going to be covering, and you should really understand these. So one is, first of all, everything in computer, you're just either reading data or like writing data or doing something like that or processing it. Each data in memory, they all have like an address, and that's often used when you want to write or read to that data entity. And they could cover multiple spaces in the address space. It depends on how big your data. And then different parts, you have different parts of a so you can represent data differently depending on how you use it, but at the end of the day, it's all bits and numbers. So just keep that in mind. So first of all, I'm going to look at, there are different types of programming languages that you probably are familiar with. So if you've been to university, you probably heard of C and Java, because these are the first two languages that you learn. And they're kind of different. Then you have another language class in the Python, or like interpreted Okay, but essentially you have three different classes of programming languages. You have compiled, interpreted, and hybrid. I think Python was supposed to be up here. But the difference between these three is kind of subtle, but they also lead to very different representation when you look at the underlying, what it compiles to. So a brief demo. So if you are familiar with this, if you have a C program, let me enlarge this. So if you have a C program like this, you have some code, and then you would have to compile it, and then you would have this binary executable, which you would then run it. You can just run it directly. But you also have other code, which is you have interpreted code, such as Python. So you have Python code, looks like that. You have code, but then you would run it with a special program called an interpreter. So here, if I would run it with this Python program, it would print out some stuff. Likewise, you have a third class, which is mainly just Java and sometimes Python. But in this case, Python is interpreted, but sometimes it can also be compiled. But essentially, you have Java, which you have code right here, but then you run it with a compiler, and then you can see that it's compiled to this class.class file. It's not a binary, because I can't just do this and run it like that, or even if I change permissions on that, this wouldn't run natively. So I would need to have another interpreter to run it, or run it like that, and then it will run. So that's the main differences. But we are actually going to focus on the first type, the compiled class of languages, because the other two are more trivial when we're reading it and trying to reverse it, usually. So yeah, these non-compiled programs are usually easier to read, unless you obfuscate it. And compiled languages, you require special tools to actually read the code and understand it. And we're just going to focus on C because that's the most simplest language, compiled language. But you can also still apply these same principles to other languages and other compilers, but they'll be a little bit trickier. So let's briefly talk about compilation is. So when we're looking at C compilation, we run it through multiple steps. So you start with something called preprocessing, which takes C code, gives output C code. What's the difference? When you output that C code, you end up having some processing. You're expanding out macros and doing all that stuff. Then you go to the next step, which is assembling it, or compiling it into assembly with the -s. And then the next step, you would then assemble it into these object files, .o files, and then you would then link it with GCC. And here you can just use GCC, but there are other tools that you can also use for various steps. So here, what we can do is see how this program that I showed earlier, if I were to compile it with -s, notice now I have a new file called test.s, and you can see this is some form of assembly. And then when I compile this, it will produce a test.o file, which is basically a binary thing. And you can see it's starting to, there's still like some of the strings that you see there, but it's like unreadable code. And then finally, if I were to link it, I then now have this binary, which I can then run. So there are different types of executables. We're going to just look at ELF because these are the ones that run on Linux. There are other formats for other OSs. If you're on Windows, you most likely are familiar. You most likely are running PE binaries. And if you have like old programs like DOS or like old DOS games or whatnot, you would have the fourth type. So let's look at the ELF format. So let's look at our first tool, Readelf, which is very useful for kind of reading ELF binaries. The format itself is actually not too complex, but as you will see, there's like a lot of stuff in ELF binaries, and a lot of them are just fluff and like stuff that you really aren't really important when you're reversing stuff. So the main parts of an ELF is the header, the program headers, section headers, and symbol table. The latter two are not really super important for reversing because they don't come when you actually run the binary. But I will discuss that more later. So if we're looking at this, so earlier I said this was the binary that was like executable. If I use readelf and do -e, you see now there's a bunch of information. So you can see this is the ELF header. There's some cool information in here. This one is AMD x86 64-bit. And then you have the sections, and then you have the program headers, and then yeah, that's basically it. Okay. So now we talked about the ELF header. I mentioned earlier it's just this. It has a lot of information. Generally, what you want to know for this is it tells where to find the program and section headers, and it tells more like information about what the ELF binary does or is. Then you have the program header, which tells you how to load the binary into memory. We're gonna kind of delve into what that means later on. The section headers are useful to whenever you have like parsers, ELF parsers like readelf or like object dump later on. But this is a slightly different from program headers. Some common sections include, you have the text section, which contains all the actual instructions. You have data section, which is like all the data within the program. And then BSS, which is useful for all the data that's initialized to 0. So globals that don't have any initialized value. And then we have the GOT and GOT-PLT data stuff, which is important for when we're starting to call functions, but not really important for right now. And these are some of the major sections. So now I'm going to start talking about GDB. GDB is a really nice tool that allows you to kind of debug these binaries. And I'd say that's one of the biggest tools you want to learn how to use if you're doing reverse engineering. GDB itself can be kind of difficult to use, so I would recommend installing a plugin like Pwn Debug or GDB Jeff. If you can Google it, it's easy. Probably is the first link to install. From my experience, I know Pwn DBG is a little bit more difficult to install, whereas the Jeff has relatively easy installation in download and installation process. And these are some of the more common instructions, that commands that you can run in GDB. I don't think you would have to. At some point, you would have to kind of understand, kind of memorize it. But right now, just you can just use this slide as like a reference. And so now we're going to start talking about what is ELF binaries, how it's loaded. So right now, I've been talking about how ELF binaries, how they are constructed. Now I want to show what they are and how it works. How are they loaded into kernel? So this is actually a very complex process, but I will just simplify it here. Simplify from what is up here. So basically, first of all, the kernel uses the program header to load in the ELF binary. It passes the arguments and the environment variables, and then it passes control to this program called the ELF interpreter. Then this interpreter is actually this other program that then does some more initialization and does some resolution with and this helps resolve all the shared libraries that the ELF binary uses. So for example, most binaries use the standard C library or glibc, and the interpreter helps to resolve that so that we know where to find the standard C library. So let me actually pause here for a second and go back to here. So if we look at this program, I'm going to use a command called file, which lets me see some information about the binary. So you can see here, this is dynamically linked, and this is the interpreter. So this interpreter is actually what is kind of being called first before this binary even runs. In fact, this file, I can even just run it like this, and then it will still run. And this is basically running the interpreter directly. But yeah, going back here, now we talk about how the heck does functions get called. So here we have if you're writing C code, eventually you're going to want to have to call some functions from other libraries. You don't want to be writing every single function from scratch every time. So there's this standard C library that is that every program loads in automatically. And how do we know how to find that function? So here we have this special routine used to resolve these functions on the time when you call it. So when you're looking with ELF binaries, you're gonna hear the word procedure linkage table or PLT everywhere. You're gonna hear that term be used everywhere, and this is what it is. So here's kind of a brief description of what that is, but I'm just gonna go use a graphic. So when we're calling the printf, let's say called printf function, it will first jump to the PLT entry of printf, which will then indirectly jump to this GOT entry, which is just an address, which then you use to jump to whatever the function printf. But at this point, it actually points back to the PLT entry, which means it'll actually then jump forward to this loader fix-up code, which will then actually do the actual resolution of the printf function, and it will then call printf, and then it'll exit. So that way, the second time printf is called, it'll actually just go to the PLT entry and then jump directly to printf. So let me do a short demo with that. So let me see if this one is. So if let me change this code, and then I believe I have to make a specific setting, no pi, because there is some, to make sure that it actually implements this lazy loading kind of thing. So let me double check. So now if I do start, I get to this main function. So you can see now we are in this GDB is now stopped on the first or like the first few instruction of main. And I want to go into this puts function. So I'm stepping into it, and then you can see now I'm in the put PLT entry, and this address right here refers to this got entry. And if I did this correctly, you will see that this address actually points to here. So if I dump the value of that got PLT entry, and that just points right here. So if I step one more instruction, it'll actually just jump to the next instruction. So now it will push, do some code, which will then jump to this link fixer thing, and you can see now it's doing some internal function, some internal resolution. Let me just do ni to step over functions. So now it's doing a lot of things. So now it calls the DL fixup function. Let me just step over that. And then at some point, now I'm at the last jump function, or jump instruction. And once I step one more, you can see now I am in the puts function. So if I type in finish, it'll basically execute until it returns from this puts function. So now I am back where I was just like an instruction after that. And you can see it printed out some text and said hello world. So if I continue stepping forward, now I get to the second puts function, except this time it will call the PLT again. This time this got PLT thing has already been set to something else completely. So if I go back a few steps, let me see if I can find it. Oh, fudge. Okay, so back up here, you can see this 404018 had this value before. Now it had this value, so it changed. So now if I step on this instruction, it'll jump to puts directly. So that's how the resolution works. So if I exit out, you can see it printed out something else. I'm just gonna finish this code and exit out. So that so let's go back here. So now I want to briefly talk about how program images. So briefly, I mentioned how kernel loads a program into this memory, and you call that a program image. So when we're looking at this, a program image is just basically all the set of sections loaded into memory, and they're usually put into segments. So here, the top part, we have the base program image that contains the text section, data section, BSS section, all that jazz. And then we have some heap after that. And then at the very bottom, we have this stack, which grows from high address to low address. And you have the heap, which grows in the opposite direction. And then you have some mmap stuff in the middle. So let me emphasize that the top is from low to high. So I can actually show that again. If I run a program and start it, I can use vmmap, which will actually tell me this is the actual program image. So you can see this top few memory segments are just the a.out file, the actual program. And then you have some mmap stuff, which is just the libc, and then you have the loader, the linker, and then you have this stack at the very bottom, which grows from bottom to top. And yeah. So now that I kind of did brief overview of like how ELF binaries work, I'm going to start going into the assembly itself. Assembly is just the human readable form of machine code, and the only difference between the two is, well, the specific numbers in the machine code actually code for whatever assembly instructions. And we have two different syntaxes for x86. There's the Intel syntax and there's the AT&T syntax, which no one uses AT&T. It's a horrible syntax. I'll show you specifically why later on, but the Intel syntax, in my opinion, is superior. But unfortunately, it is used by GNU programs, so we have to live with that. So here's like an example. So you have this move. Generally, when you're looking at assembly, you have some instruction name, which is usually like a abbreviated form or a mnemonic of some actual command that you would expect. So like MOV is just short for move. And you can see this is a move is just basically you're assigning one value to another value. So you have this RBX plus 10 with brackets around it. And then you have RAX here. And then on the other hand, you have this, which is AT&T syntax. You have this hex 10 percent RBX register, and then you have RAX. So the difference between the major difference between the two syntaxes is when you look at Intel, you have destination and source, while AT&T is like source and destination. So an easy way to remember how Intel syntax works is that you can think of it as like an equal sign. Generally, when you're looking at destination source, is like an equal sign when in like any other language. So like RAX is equal to this value right here. And generally, both of these are the same, do the same thing, and they code exactly the same. And what it's doing is it's moving a value at the memory location RBX plus 16 into the register RAX. So this is, if you're familiar with C, this is like the pointer arithmetic operation stuff. Oh, and another thing to quickly note is in AT&T, generally they have some suffixes that represent the size of the operands, these operands. And Q is like Q word, quad word, which is basically the 8 bytes move. 8 bytes for 64-bit. So yeah. So here are some important instructions. Again, you can also use this as like a reference. They generally should have mostly instructions that you encounter in like very common code, C code. So we have the push and pop. So you have that pushes some value from the stack and pops a value from the stack. And I believe the stack, we will kind of mention what it is later on. And then, so then we have the stack argument, stack operations. Then you have the move instruction, which we saw earlier, which is just assign a value from one place to another. And then you have the LEA, which is, in my opinion, very confusing at first, but it actually makes sense. It's actually a very dumb instruction, so it actually does less than what you think it does. So the very simple way of saying this is just dest is equal to address of SRC, where bracket SRC is like a memory operand. But all it's saying is just you just assign destination to the source if you remove the brackets. So it's never going to dereference memory. I'm not sure what that was supposed to say. Oh, yeah, I think I did okay, ignore that. But it's essentially when we're looking at LE8, it's just basically this, it just copies the value from SRC into dest if you remove the bracket. And the reason why we have this is because you can have very complex operands, memory operands, where you have like REX plus RBX times 4 or something like that. So this, the usage of this is just, you can do very complex arithmetic operations in one instruction. x86 just gotta be like that. So then you have the actual arithmetic instructions. You have the add, subtract, multiply, divide, XOR, shift left, shift right. Essentially, most of these kind of act like plus equals or minus equals if you're looking at any other language. C like language. That's how these operate. Because you have two operands. One of them is the destination, one of them is the source. Then you have the call instruction, which you can use to call a function. And you have the respective return, ret, to return from a function. So these are, when you're calling and returning, these do not actually implement how you're going to pass arguments, nor how you're going to return values. That is done in a different mechanism. But all this does is it allows you to do some task and then come back to that after you're done with that task. That's all these two instructions do. And then you have the jump instructions. You have jump, which lets you jump to some other location. You have some conditional jumps, JLE, JGE, which very obvious, is just if you jump if it's less than, or jump if it's greater than, etc., etc. And then if you want more kind of examples, you look at this, go to this source right here. And while I mentioned that we will release the PowerPoint after this presentation. So now we're going to go to actually mention what flags does. So this is where flags register come in, is because since all these jump instructions, they're only taking one argument, which is the location where to jump to. How do we know like some, if we're like doing some what we're comparing with less than, that's less than or greater than or equal or not equal. So this is where flags come in, is these particular instructions use the flag registers to determine whether to jump or not. And depending on what flag registers are set or not set, they will jump or not. And how do you set the flag registers? Well, you set the flag registers using the test and compare instructions. Or most of the arithmetic operations also set flag registers. But these are used if you just want to set the flags. So test allows you to do like a bitwise AND on the two operands. Generally, you use that if you want to test if something is 0 or something like that. Then you have the compare instruction, which you can use to basically do comparisons. So like arg1, if arg1 is less than or arg2, then the next jump JL or JLE instruction will actually jump. And essentially what it does internally is just computes the value arg1 minus arg2 and then sets the flag based on the result of that. And this is why AT&T syntax suck, is because when you're looking at comparison, and all the AT&T syntax, they swap the two arguments around. So it will actually be compare arg2 minus and arg2 with arg1. And what happens is, if let's say you have like a jump if less than, right after this compare, you actually have to see if you're looking at it, you actually have to swap like the kind of the less than or to greater than in order to actually make heads or tails of what it's actually comparing. So this just adds a little bit more confusion. That's why AT&T is kind of hard, kind of more work. So now we start to talk about stack and heap. So I mentioned stack many times now, but this is what stack is used for. So think about it. You have stack, which you use local variables, where you define local variables, versus the heap, where you're just allocating some memory and then deallocating it, or if you're creating objects or freeing objects or something like that. So the reason why you would use a stack to store local variables is sometimes I might be calling the function multiple times. So let's say I call like a recursive function. I don't want the variables from my first recursive call to this function to mess with the second recursive call. So the variables are actually two sets of different variables, and they don't interfere with each other. And that's how a stack will operate. And in the next slide, it'll actually talk. We're going to continue to kind of figure out what the stack is. So if we're looking at stack, so we now talked about stack frames. Essentially what a stack frame is that the space of stack that a function uses. So each time a function is called, you create a stack frame. And you have this, and when you're looking at functions, especially if it's compiled from C, you have this prologue and you have this epilogue. You're generally going to see that unless if the function is optimized. But normally you're going to see this push RBP and then move RBP to from RSP, and then at the end of it you have a leave, and then you have ret. So this is basically standard. Every function has it. So like those parts are probably not important when you're reversing. And then this sub RSP hex 10, that allocates the amount of space for the stack frame. And the way how to pop out of the stack frame, so remove that stack frame after we exit out of this function, is we actually save the previous RBP, and then we save the bottom of the stack, our current stack frame, onto this RBP register. And then when we leave, we actually move the RBP back into RSP so that we move up the stack frame, and then we pop the old RBP. So then when we return from this function, it's as if nothing happened. When we're talking about the stack, how the stack looks. So this is kind of how it would look when you call multiple functions. So you start with you always start with the save RIP, which this is automatically created every time you use the call instruction. And then you have the save RBP when you push RBP to stack, and then you have the local variables, and then and then you call a function, and that function saves the RIP again, and then the RBP then points to this the stack frame of the previous outer function, and then you just keep like pushing stuff down every time you call a new function, nested function. And then RSP would be at the very top of the stack. So now, previously I mentioned that call and ret instructions don't actually do anything for like arguments and return values. So now we're going to talk about how do we pass arguments and how do we return values from functions, because obviously in C sometimes we pass in arguments so that we can tell the function, hey, we want to compute this particular subproblem with these arguments inputs, and we want some output in this particular register or something like that. Or we want this particular output for this particular operation. So when we're looking at inputs, arguments, we have this order of registers that we pass it in. So we start with RDI, RSI, RDX, RCX, R8, R9 in that order. And then if we have any more arguments, we pass it on the stack. And then when we return a value, we return in the register RAX. And every time you call a new function, you're going to have to always preserve RBX, RSP, REP, and R12 through R15. So that means if you use it whatsoever in your program, you would have to preserve it by, let's say, pushing the register, the old value, to stack before you modify it. And this kind of calling convention is called the system V, and it's mainly used with Linux. I think Windows has its own calling convention. But yeah. So now that I've covered all the basics for reversing, let's look at a demo where we're going to kind of start reversing some of a small challenge binary. So so generally when we're looking at reversing engineering, you want to first do some basic like stuff about it to kind of figure out what you're doing. So like, let's say you want to figure out like how to run it. So am I working with an ELF binary? Is it like a Java binary? Is it like a Windows binary? What is it? How do I run it? And then we're looking at stuff that some information that we might get that might help my analysis. And then maybe you can use that to find locations in the program that are useful. And then maybe from there we can figure out what is this function doing. And then we start going deep into the rabbit hole and then start kind of dissecting this program apart. And then just continue doing this until we basically finish the entire, figure out what the binary is doing. Maybe we get the flag, maybe we get a password, whatnot. So let me, so here I will actually, what I will do for everyone that is on the chat, I will actually upload the binary that I'm looking at, so everyone can work along with that. Let me see if I can find it. Okay. Okay, yeah. It's called a.out. So I think this is correct. So first thing, what I would like to do first, I would like to know what this binary does. So a really good like command to run first to figure out what type of file we have is just file. And then we can see here it's a 64-bit executable and looks very standard. It's not stripped and is dynamically linked. So that kind of information tells me maybe I could just reverse engineer this. It's a 64-bit binary. So usually at this point what I would do is I would pop out IDA, but in this case is actually not too hard. You can probably just look at the assembly. So let me start using another command called object dump. So object dump, you want to pass the -d flag, which is useful for disassembling everything, and then pass the file. And now you get a bunch of code, and you're gonna be like, what is all this stuff, all this junk? And I'll just tell you, a lot of this junk isn't actually useful. So you see all these functions called fini, libc, csu fini, libc, csu init. This is like completely useless. 99% of the time, this is not going to be important. 99%, this is just like standard like fluff code to make it run properly. So like you see all these code, dereg, all these things. Most of these are just basically they're there no matter what kind of program I compile. So really all I need to care is, and also up here these are like the PLT functions I mentioned earlier, and you can probably guess what these functions do just from the name of the function. So all I really care is this function right here, which is a interesting named function, and this function right here, which is also very interestingly, which is the main function. Yeah. Also, in case if your output actually looks different from mine, I actually did something interesting. So I actually aliased my object dump to this command right here, object dump with -m Intel, which makes it object dump to always output Intel syntax. I just like Intel much more, so this saved me a lot of hassle. So that's if you wanna just always use Intel. So let's start looking at this program. So usually what I would like to do is always start from the, it might be good to start from the main function, one approach. So one approach, I could just start from the main function, and let's look at this. So the first function, this looks very, very small. And if we look at what the prologue and the epilogue, this looks like the epilogue, the standard epilogue, and this looks like the standard prologue right here. So really, we only have 3 instructions that is actually doing something. When you say follow along with this file, do I need to upload it into anything? Oh, you probably want to put this inside a Linux machine, so that way you can have like tools like object dump. So what you could do is I would kind of copy the link, and you can just, if you're on a Linux machine, then you should have wget install. So then you just download it that way. That's the thing. And then if you download it, you'll see that, hey, the file is created. And then you might, if you want to be able to run it, you want to add it with the execute flag. So that way it actually turns green in my terminal. But it lets you to execute stuff like that. And then you can run object dump on that. Depending on what distro you're using, you may or may not need to install something, but it should tell you what you need to install. But going back here, yeah, so this is that function. So let's look at go back to main function. So we have 3 instructions that's actually doing something. And actually it looks like this one is actually not that important. This one's not that important. This looks like it's just returning the value 0 from main. So all it's doing in this function, main function, is calling this one function called I'm about to do some surprises. So then we look at this function and we look at, see, hey, this looks a little bit more complex, but it's actually not too bad still. So let's look at this piece by piece. So what's it doing? This looks like, again, this looks like a prologue. This looks like the epilogue. So we don't really care about that. Nop is just a no operation instruction. So that really, we can basically, let me just copy it like this. Copy it into text editor. So this one looks like not important. This one, not important. So now we have the meat of this function. So right now I'm using also a tip for like reversing when you're looking at assembly. Right now I'm using a text editor, but I highly recommend, if you have the paper, just print out it on a sheet of paper, and then you can scribble all over it or write it or do some like draw arrows to help. Especially it helps with the control flow. And that's kind of how I started out. So here, the first part we're looking at is this first 3 instructions that we see here is calling this function printf, and then it's passing in one argument. How do we know that? Is because RDI is the first argument in like the call convention, systemd call convention. So now we can see this LEA instruction, which is what I mentioned earlier. And all this is doing is calculating some arithmetic operation when you take RIP plus this value, this constant value right here, and Objectum actually does a lot more for you, and it actually tells you, hey, this is just 2004. So the address 2004 relative to this binary. So I can just say this part is just printf 0x2004. And then let's look at the next part. This part, what's it doing? This one, it's calling fgets. Okay, so let me start looking at the arguments that it's passing in. So you have fgets. So RDI, which is assigned from RAX, which is from this from this move from here. So we can see this looks like it is, again, this looks like RP plus some constant, looks like it's taking in from some relative to this binary. So it looks like it is referencing this address hex 04050, and that's std in. So we can actually just say this is, oh wait, oopsies, I must have misread the line, but this is RDX, which is the third argument. So let me, my bad. I meant to look at this one. So we see how RDI is assigned from RAX, and RAX is assigned here. But then what is this RAX doing? So it looks like it is passing in this value. It's setting RAX is equal to RBP minus hex 80. So let me just put it there for now, and we can figure out what that is later. And then we have this one, which is ESI, is assigned to the constant hex 78. So we just pass 78 right here. And now we have this fgets with 3 arguments. So might kind of, if you're not very familiar with C, you might ask, what is fgets? Of course, you might know what printf does. It's probably some sort of print function, or it outputs some stuff. But fgets might not be familiar initially. So I always recommend looking at a man page. So fgets, if we're looking at this man page, we can see there's a lot of functions that are very similar, and it just input characters and strings. So fget reads the next fgets, my bad, reads in at most one less than size characters from stream and stores it into buffer pointed by s. So if we look at the fgets, the function, we can see the first argument is a char pointer, which in fancy text also can be called a buffer. You have some size parameter, and then you have the file stream, some file object. And we can see that's what it's doing right here. So we have fgets, and then this is actually some char buffer. And then this is the size of that buffer. And then we have std in, which is the standard input. So here we're just reading from standard input, and then we're moving it into this buffer, this buffer located right here. And if we remember before, we look at if we remember, RBP is actually some the base points to the base of our stack frame. So here we're actually referencing somewhere inside our stack frame. So that's actually, so RBP minus hex 80 is some local variable that we defined. So let's go on to the next instruction, or next set of instructions. So now we're looking at here. We're looking at this str compare CMP, str CMP, and let's look at man page again. So this one compares 2 strings. It compares 2 strings. The comparison is done using unsigned characters. If it returns an integer indicating the result, so 0 if s1, s2 is equal, a negative value if it's less than, a positive value if it's greater than. So basically this tests if 2 strings are equal or not. Very useful. So let's look at what arguments is being passed in. So we look at the first argument, which is RDI. We can see this is again some Lee instruction, and it is now in the address 200B. So strcomp 0x200B. And then we're looking at the second argument is from RAX, and RAX is equal to this value. Another Lee instruction, and if we just copy it, it's just RBP minus hex 80. And remember, that is basically our local variable from right here that we read input from. So what we can gather here is actually just comparing our input with some string. We don't know what that is yet. So then we look at the next part. So now we know that this compare is put into the register EAX or RAX. Oh yeah, I forgot to mention one thing about registers is you have this register RAX is the same thing as EAX, other than the fact that EAX is a 32-bit register and RAX is a 64-bit. So there are equivalents of a particular register that refer to the same register, but they are different sizes. But yeah. So if we're looking at this, we now have that test instruction that we mentioned earlier. So test EAX, EAX. So what is the meaning of this? So we can see that if we AND EAX and EAX, we are just, if we're doing the bitwise AND of EAX, EAX, it's just equal to EAX. So then it allows us to determine whether if this is 0 or non-zero. If it is 0, then it sets the 0 flag. Otherwise, it does not set the 0 flag. So what do we remember that 0 corresponds to in strcomp? If we go back to strcomp, we can see if the result is 0, then we know that the two strings are equal. So we can see here, it's doing some kind of, it's testing some whether if the two strings are equal or not. So here we have that jump instruction. So jump if not equal. So if it's not equal, then you will jump here to RBP. And we can see that if it's not equal, it will do some LEA. It will take some address and then it will write that. Otherwise, it will fall through this jump instruction, and it will just puts on something else. So you can see here what this is actually doing is if this is equal, it prints something. If it's not equal, it prints something else. So now I think it's time to figure out what are these addresses right here. So another way that we can figure out what this is actually, these addresses are, what these addresses point to, is I can now object dump it, but instead of doing D, we can do -s, a.out. And then now we can see a bunch of other data. So now we can see it's just, if we do a -s, now we see it's just a hex dump of all the data, all the sections in this binary. So let's go to our 2004 where that is. So now we're at 2000. 2004 is right here, starts here, and you can see this prints out, this is a string with flag and then a space. So this one, if we're looking at this, this says, this prints, let me just do this. It prints the string flag right here. So let me erase this out because that's not really important now. So then we look at this next part. So this is just fgets, it's reading some input. So now we have the strcomp where it's comparing input right here and with some 200B. So let's look at 200B. So B is actually the hex for 11. So if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or let me just count from here. Actually, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B right here. So now we can see this string right here. So this is actually our secret string that we are trying to compare against. So if I just copy that, you have that string, and then the next part is if it's equal. So if let's say this is equal to 0, so it will just fall through here. What will it do? It will put with this string right here 1F. So 1F is that last thing right here. So this will just print out correct. You can see that's last C, and then on the next line it's just correct. And then otherwise, it'll just put on 2.8, which is right here, which is incorrect. So right here, we basically just completely reverse the entire code, turn it back into C, and you can see if I type in this. Now let's run it to confirm that. Let's see. So now we can see, oh, it's just printing out the string flag and space and telling me input something. So if I type in some text that's not the flag, you can see it prints out incorrect. So otherwise, if I copy this string, it will still be incorrect because I probably screwed up. So let me do this. Okay. So here because I didn't clear out the new line. That's silly of me. There you go. I totally screwed that up. But you can still see if I input the flag correctly without a new line, it will print out correct. So that is one way you can solve it. So this is like the most traditional way. I'm just going to go brute force every single code, figure out what it's doing, but it's often very slow. So I want to take shortcuts if I can. If I do this, strings a.out. Strings will print out every single string that's in the binary. And you can see, oh, shoot. The flag is actually inside is actually a string. So now I can just copy that and just submit it right there. Very easy. So that's one. You could use tools like strings to help you like quicken that that process. And next week I'm going to kind of show how to use Ghidra. I think I'm already very over time, but I have one last slide. So again, this is like this next slide basically kind of breaks down what I mean by how to do these steps. So again, first you want to run some tools like binwalk, Readelf, etc. Then you look at strings. That's very important. Even if there's not like actual flags in there, it helps you. It also helps as like signposts. So like you can figure out if it's printing this thing at this point, then you could just kind of figure out, deduce, oh, this might be the right path or this might be the wrong path that I'm going. And then at that point, you also want to start then kind of looking at some easy functions to reverse and start from those and then go work up. And here, then finally you just do the rest of the owl to solve it. And yeah, that last step is probably the hardest step. But yeah, and no, we aren't going to go with that demo because it's already over time. So references I have here, there's like links to everything. Let me actually upload it. I might does anyone have any questions? I know I'm a little bit already very over time, but if anyone has any questions, I can just answer at this point. And if you don't want to like talk, you can always just put in the stream chat. How has my day been? Well, it's been all right. Thanks for asking. Cool talk. Well, yeah. Thanks, Jerry. Well, I guess no one has any questions. If you end up having some questions when you watch this finally, maybe next week, sometime before next week, I will. I can also just DM me. I can answer that at that point. Is next week Ghidra and CTF? Yeah, next week we're going to hopefully look at some kind of more practical like reversing challenges and actually maybe work with Ghidra and whatnot. Work with all the other tools. Oh, before I stop, let me also show how you would install the Pwn debug or Jeff. So if I just search up GDB Jeff, you should be able to get a pretty quick. The first one or the second, probably the second one, you will have. This will get you to the GitHub link, and you can see all these beautiful kind of code that you can just copy paste to install. Don't worry about the fact that you're running code that you download from the internet. If you're downloading Jeff, you're already doing that. But yeah, this one looks very not conspicuous. That's how you. If you just run this program, run this line, that's all you need to do to like install GDB Jeff. It's pretty much that simple. From my understanding, Pwn debug is a little bit more tricky because they have a lot of other dependencies, but I believe they have like a script that you can use to set up and install. So yeah, you have to clone the Pwn dbg repo, and then you run the setup sh script, which installs a bunch of stuff. How did I find the path to the a.alf? Can you be more specific? What do you mean path? I don't think I can hear you unless something's wrong with my Discord. Oh, that. Okay, I don't think I can hear. That's weird. But you can still see my windows, which is even more weird. I think I know why. I think it's. I think my browser is just being dumb, and it's not actually. Yeah, I see that you're talking. I can't hear anything. I think the browser is just being dumbass. Yeah. Yeah, I can't hear a single thing from stream chat or from stream. But are you talking about? Yeah, I can't hear Jerry either. I can't hear anyone. Oh, the path. Let me just do this way. So if I'm looking at this file, right? If I right click this, just copy the link, and then let me move this back, and then I just wget and then paste that link right there, and that's how I got the link. And wget just yeah, it downloads a file from like a link, and it's very easy. It's I think that one of the easier tools to work to download something from the internet if you want to directly copy that into like some terminal. Yeah. Let me stop sharing. Let's see. Does anyone else have any other questions? I probably need to use the chat because I can't see anything, hear anything. Let's see if I can find what the root issue is. Okay. But if there are not any other questions, I think I'll just end the presentation here. Okay. Well, bye everyone. Okay, let's